All right. Thanks and welcome to this session. And actually, I have two presentations in this session. This is the first one. It's titled Effects of Nanomaterials on Engineering Performance of a Siliconate-based Sealer for Cementitious Composite. And my co-author, collaborators, my PhD student, Mr. Zhipen Li. Now, here's the outline of the talk. We'll start from introduction, why the issue is important, and what's innovative, and then move on to experimental program results and discussion, and then conclude, talk about future work, and also acknowledge our collaborators and sponsors. So you can see at the bottom left, it's an anti-icing chart putting down liquids to facilitate snow and ice control on roadways. And then in the middle is a de-icing chart putting down solids. So these typically use a lot of chloride salts as freezing point depressants. And the unintended consequence is they actually will compromise the durability of concrete infrastructure, be it bridge deck or bridge column or so on. So for instance, a recent study we published in ASC Journal of Materials and Civil Engineering revealed that the presence of salt not only accelerate the physical damage of concrete, but also induce some chemical attack. Basically, what you're seeing is at the macroscopic level, you see formation of new crystalline phases, which could be Friedel salt or calcium carbonate. These kind of things are forming because you're losing the calcium ions out of the CSH gel, which binds the concrete together and gives it the strength and durability. So this is a phenomenon known as salt scaling, but we're giving it a little bit new meaning because traditionally we would think salt scaling is a physical mechanism, but there's also chemical attack. So how to deal with this kind of distress? First, one of the tools in the toolbox is surface treatments. If we can keep the water out, keep the salt out, we probably be fine with the concrete. So surface treatments such as sealers or hydrophobic treatments, they can work well in effectively protecting the concrete from salt scaling and extend the surface life of concrete pavements, bridge decks, and so on. And there are three categories of products. First one is barrier coatings, epoxy, acrylics, they basically form a film on the surface of the concrete. Another one is hydrophobic impregnation, which are typically silanes or siloxanes. They can be effective for typically 3 to 4 years. You can almost envision them as some sort of vegetable oil, right? They penetrate into the microstructure and help keep the water out. The third one is pore blockers. These are silicates or soil methyl esters. They will basically block the pores instead of forming a film on the surface. So in recent years, we have evaluated some of the products on the market. I mean, mostly the popular products used by state departments of transportation, and some of the research are in these two papers. Again, the sense of urgency is because we're increasingly addicted to salt, road salt, and we're using more and more salt on our roadways. Now, one interesting sealer is PMS, or potassium methyl silicate, which is a surface treatment, hydrophobic treatment for wood and cellulose and so on. But we think there's potential of using this sealer for concrete because it seems to work like having the three aforementioned functions in one. First, it will form a membrane by reacting with airborne CO2, so you have a membrane or barrier coating. Second, it also provides a hydrophobic treatment, so it's the second mechanism. And the third one is it also works as a pore blocker because it forms certain products that will block the pores. So it's kind of like 3 in 1, a pretty good deal. Now, arguably, nanotechnology can further enhance the performance of such sealers. For instance, we know in recent years, nanoengineering or nanomodification of cementitious materials seem to work really well. When you add typically 1% by weight of binder, you can significantly reduce the water absorption, gas permeability, and water permeability of such cementitious materials. And then graphene oxide is a novel two-dimensional nanomaterial. We have previously published a few papers looking at this as a multifunctional admixture for geopolymer or ordinary Portland cement concrete. And also it could work as an effective surface sealer for concrete by itself because of its two-dimensional structure. Basically at the nanoscale, you're forming nano sheets, which blocks out the ingress of water or oxygen or CO2. So in this study, our hypothesis is that the admixed graphene oxide and morenonite nanoclay can provide the PMS sealer with better performance through the following mechanisms. First, to modify the PMS sealer and improve its hydrophobicity through nano micro roughness, forming some sort of assembly of nano and micro structures. And the second one is the nanoclay could react alkaline PMS sealer to generate KSH gel or potassium aluminum silicate hydrate gel to refine the microstructure of mortar matrix. We're talking about the pore blocker mechanism, right? The third one is the GO may catalyze this process because we know on the surface of these GO nanoplatelets, they carry a lot of negative charges with very desirable chemical groups such as the hydroxyls or the epoxy or the carbon oxygen double bond. So in this case, we took a penetrating sealer, which is commercially available. The chemistry is based on PMS and a little bit siloxane resin. And we, of course, run the FTIR infrared to look at its chemical composition to make sure it's truly a PMS mixed with siloxane resin. And that is the case. And then we also take nanomaterials, again, nanoclay or morenonite nanoclay is the most affordable nanomaterial on the market. I think its price is about 6 or 7 times the price of Portland cement. So it's very affordable, and it's got its unique properties. The reason it's calculated as nano because once they're well dispersed, one dimension of the nanoclay platelets is only a few nanometers, but of course the lateral size is in the 20 to 25 micron size, range. And then graphene oxide itself, again, because of the presence of a lot of oxygen containing groups, there's about 26% oxygen atom, and the lateral size is about 4 to 20 microns. And it carries a lot of negative charge on the surface. That's why the zeta potential is about minus 30 millivolt at a neutral pH. And you can see when you disperse, say, 0.1% of the graphene oxide in the water, it basically turns itself into a black ink. So it's a solution, not a suspension, and it's well dispersed. So there's no dispersion issue. And if you look at the scanning electron microscope photo on the bottom right, you can imagine it's basically at the nanoscale, this kind of paper crumbled or wrinkled a little bit. If you actually shrink a piece of paper or a typical 8x11 paper by a million times, that's what you get at the, basically that's your graphene oxide, which has very high surface reactivity. Now, in terms of the nanomaterial being dispersed, dispersion is always important. So we relied on ultrasonic dispersion. We start from, exploration of what dosage of graphene oxide will be ideal by mixing it with 0.1% nanoclay. And we, by looking at the water content angle, which gives us an indication of surface free energy, we selected 0.06% as the right dosage for graphene oxide. And then we further use that to explore different dosages of nanoclay, and the optimum one turned out to be 0.15% by mass of the sealer. So then the symbols here, the very last one, 15N corresponds to 0.15% by mass of, the nanoclay, and 6G is 0.06% of the graphene oxide, and P stands for the PMS sealer. So here's our mixed design. This is a concrete with a little bit low water binder ratio, 0.365, and 4.4% air content. We're talking about 2x4 cylinder for compressive strength testing. And it's more cured, and then the sealer was sprayed onto the mortar surface at this dosage, concentration. It's approximately 1 gallon over 300 square feet, which is the recommended range by the vendor. And then this sealer had to dry in the air for 2 hours to react with airborne CO2 to facilitate its curing. So we conducted a number of tests, water absorption, gas permeability, water contact angle, and penetration depths, which relied on a staining test. And then we also conducted a salt scaling test, basically simulate the deterioration in an accelerated manner in the lab. And then the high resolution microscope and the thermal gravimetric analysis help us to further understand the mechanisms. Now, in terms of results and discussion, again, we've mostly focused on this best performing nano-modified sealer, which had 0.15% nanoclear and 0.06% graphene oxide, and they together worked really well, reducing the hydrophobicity of the surface of the membrane, and also that can be translated to reduced surface free energy. You can see without any sealer, your water contact angle on the left bottom is about 30 degrees, and with the synergistic effect of these two nanomaterials, you bump that up to more than 120 or 130 degrees, which is still not super hydrophobic, but it's really beneficial. As you can see later, this significantly increased water contact angle helped keep the water out. Now, in terms of the mechanism, there are a number of them. It's kind of hard to differentiate some of the possible mechanisms. The figure on the left is figure A, indicating the sealer reacting with CO2 and forming a membrane on the surface. Basically, that extends itself to figure B, which is before the sealer was on the surface of the mortar, you basically have a lot of hydroxyls on the surface, and the mortar surface is hydrophilic. But once you have this membrane formation on the surface, then it turns itself mostly to methyl groups, which are hydrophobic. That's why, from 30 degrees to 120 some degrees. Now, another mechanism is because these nanomaterials could help form nano cavities, which will entrap some air bubbles and make it hydrophobic. The figure D is basically some of the nanomaterials are not always well dispersed, so they form microstructures. So the combination of nano and microstructure form this lotus effect, with micro and nano and entrapped air. So you got this hierarchical structure that basically is known for be responsible for the lotus effect or keep the water from penetrating the surface. And very last mechanism could be, the template effect by these 2D materials, both the nanoclear and the graphene oxide. In that case, the formed KSH gel or the gel basically will be different because of the template effect. So that also helped reduce the surface free energy and the water contact angle. So this is proven by the macro scale testing. For instance, we follow the STM test protocol to measure the water absorption. You can see, in the control one, without any sealer, you basically have two phases. The phase one is responding to water soaking into micro cracks and fine pores, and the second phase is really water getting into the air voids. Now, with the nanomodification or the sealer presence, all of them only show the first stage, which is, in other words, it takes much longer to fill up the microstructure with water. And the benefits, if you look at the right-hand side, actually we show all of the nanomodified sealers we played with. On the left-hand side, we only took a few representative ones, but both of them tell the same story. The mortar surface was densified by the presence of the nanoclear and graphene oxide. And this also the reduced water absorption is also attributable to the increased hydrophobicity we mentioned earlier, from the water cutting angle change from 30 degrees to 120 some degrees. Oh, by the way, this reduction is quite notable. We're talking about 70% reduction in water absorption. Now, similar results were observed on gas permeability. Again, we attribute that to the densified microstructure. Again, it's up to 71%. And the benefit of this is now you're dealing with a surface which is much less permeable to gas interfaces such as CO2, oxygen, or moisture vapor. So in other words, this is beneficial for the durability of the concrete. Now, because of those, things we observe in terms of, reduced water absorptivity, reduced gas permeability, what you see in the soil scaling results is again, compared with the control, even compared with the PMS sealer, this nano-engineered sealer gives us much better protection. For the concrete to have the least mass loss in this soil scaling test. And also, if we look at the scaling depths, we see this relatively good linear relationship between the scaling depths and the mass loss. So compared with the control without any sealer, the scaling depth is reduced by about 48%. What's interesting is also the scaling is much more homogeneous when we have this nano-engineered sealer. Now, of course, nano-engineering has one unintended effect, which is the sealer became more viscous and penetrates a little bit less. So to deal with this issue, of course, we can play with, modifying the viscosity of the sealer because it's a water-based product. We probably can add more water, and also we can, in engineering practice, we can use a vacuum to help, accelerate or improve the penetration depths of the sealer. Also, we explore the relationship between the gas permeability and water contact angle and the water absorption. On the left-hand side, you can see that this 3D contour plot basically shows that a decreased gas permeability and increased water contact angle together will give us the lowest, water absorption coefficient, which on the right-hand side shows like once you reduce water absorption coefficient, you reduce the soil scaling loss. So that's what we desire. But again, if we were to develop a more reliable, accurate model, we need more data points. But this points us to the right direction for R&D. Now, the thermographic analysis also tells us some insight or shed more light on what's going on inside the nano-modified sealer. On the left-hand side is the residual weight over, the axis is the temperature. As temperature increases, of course, you're losing some of the components will decompose. So on the right-hand side is the differential of the TGA data, and which is more friendly to the reader. So basically what's telling us is the PMS sealer preferentially reacted with admixed nanoclay to form KSH gel, which is the yellow peak on the very left of the right-hand side graph. And then we're seeing much less potassium bicarbonate because, again, the sealer mostly reacted to form the KSH gel. So this basically indicates the sealer was truly chemically reacting with the nanoclay. And then, of course, there are some other details. For instance, there are 2 additional peaks, basically giving us some insight about, 2 types of chemical groups, and especially the oxygen to methyl and silicon to methyl groups. And it's interesting that at day 1, the graphene oxide was still, tightly bonded with the oxygen methyl group until much later, that bonding slowly disappeared. So to conclude, this study demonstrates synergistic effects or benefits of modification by nanoclay and graphene oxide to the potassium methyl siliconate-based sealer. The mortar coated with this 0.15% nanoclear and 0.06% graphene oxide with the PMS sealer represent the best performances, featuring water content angle 120 instead of 32 degrees. And reduction of approximately 70% was observed in both the water absorption coefficient and gas permeability coefficient of mortar, compared with the 38% induced by the original sealer. And after 8 rapid freeze-thaw and wet dry cycles in 3.5% sodium chloride, this sealer saw a 1.9% mass loss instead of 3% mass loss for the original sealer protected mortar, or the 9.5% loss for the unsealed mortar. So indicating better protective performance. And also we saw much reduced scaling depth. In terms of mechanism, one of which is the hydrophobicity, as we mentioned. The other one is refined micropores. Again, the right direction for further optimizing the sealer is try to achieve lower gas permeability and higher water content angle, because together they can lead to lower water absorption coefficient and therefore better resistance to salt scaling. And the future work, remember this is on mortar samples, so we could move on to larger scale concrete and long-term performance and look at life cycle assessment in various service environments. And I'd like to thank the National UTC Charity for funding this work, and also for the donation of some of the materials by BASF. Dr. Jin Zhong from Harbin Institute of Technology provided the graphene oxide, and we recently filed a provisional patent on this technology, and we're continuing this line of research. Most of this work has been published very recently, actually still not online yet, by SE Journal of Materials in Civil Engineering. And with that, I welcome your questions. Thank you. How are we doing with time?
Thank you so much, Dr. Shi. I really appreciate it. I do not see any question in the chat box or in the Q&A box, but I do have one quick question for you. How are the longevity of these materials and how long they would last on field application?
That's a very good question. We do anticipate by design, these things are UV resistant and they're more resistant to abrasion. So mostly they're penetrated into the concrete, so they're not quite exposed on the surface. So they should last longer than the products out there. And that's actually our next step, is doing further optimization, further evaluation, as well as some field demonstration on campus.
Nice. And how would be their performance in cold region?
Right, that's exactly why we started from salt scaling, because if they can do well in salt scaling, then they should do really well, in the cold climate.
Nice, thank you so much. Again, I do not see any other.
I have one.
Sure.
I want to understand exactly what the 120-degree angle to 32-degree angle. What is that? I missed it.
Right. So basically, by the time you get to more than 150 degrees, it's called a lotus effect. So a water drop on a lotus leaf won't penetrate in; it will roll off. Right. So the surface is super hydrophobic, and for a typical wood or concrete surface, it's hydrophilic. You drop a water drop and it will penetrate in, soak in very quickly. So we're trying to shift it towards keeping not only the liquid water out, and also if you see the gas permeability, we're trying to keep the vapor moisture out as well. As you probably know, when we keep the water out, then 90% of the durability issues go away.
Yes.
For concrete. Yeah.
Thank you.
Thanks.